Number 4. You have 6 pairs of socks in a drawer. Each pair is a different color: red, blue, yellow, orange, green, and purple. You can underline some important things as we go. You pull one pair out of the drawer and do not return it to the drawer. That's kind of important here, so there's no replacement. Pull one pair. Then you pull out another pair. So we've got multiple draws here. What is the probability that you will pull one pair of red socks and then, so this and word, one pair of blue socks? So 6 pairs of socks, all different colors. 1, 2, 3, 4, 5, 6. Yes, all of them are different colors. You pull one pair and you don't return it, and then you pull another pair out of the drawer. So we want to know the probability that the first pair would be red and then the second pair would be blue. So probability of red and then blue. So we want to know the probability of red, and then we're going to multiply the probability of red times the probability that remains of one being blue. So I love to see dependent, I can tell already that this is dependent because there's no replacement, no replacing socks once you pull them, which means that our chances, probability will change for each pull. Sorry, my hand writing is not very good. So I like to see this sort of problem with a tree diagram. I think it helps to think about things. So I'm going to put red, blue, yellow, orange, green, and purple. I actually think I need a separate sheet of paper. Sorry. Red, blue, yellow, orange, green, and purple. Red, blue, yellow, orange, green, and purple. And so if my first straw is red, the possible socks that are left in the drawer, there's 5 possible socks, and it's all of these: blue, yellow, orange, green, purple. And for each of these other options, there's still another 5, 2, 3, 4, 5. It would just always be the option that isn't being used here. So for example, if I first pull green, my other options are blue and red and yellow and orange and purple. 2, 3, 4, 5. So I can see that I've got 6 times 5 possible outcomes. So 6 times 5 equals 30 possible outcomes for a 2 sock pull. And what's the chances that I get red first? That would be 1 out of 6 possible outcomes. And then after that, there's only 5 possible socks that remain in the drawer, so it's just 1 in 5 chance that I get a blue sock. So if I multiply and I find a fifth of a sixth, well, that's going to be out of 30 total outcomes, 1 out of 30 possible outcomes. 1 out of 30 possible outcomes. And I think this can also be, you know what's really tricky? I'm so tempted to show the possible outcomes in a table, but the reason that you can't show all possible, correct me if I'm wrong, can you show all possible outcomes? I'm not sure that you can. The lights just went out. I'm going to explore this a little bit more and get back to you on that. I was thinking you can't use this, but what do you think? I think the reason that I was thinking you can't use the table for dependent events is because red, blue, yellow, orange, green, purple because for red there's only 5 possible outcomes: blue, yellow, orange, green, purple. Maybe the way we need to use this is different. Maybe the way we use this, because I love that this shows us there's 30 possible outcomes, and we know that there are 30 possible outcomes. but maybe we need to use this as red, blue, red, yellow, red, orange, red, green, or maybe we need to just add an appropriate, like add all the colors on the outside. We could add red, red, and then we could say this is not a possible outcome. So we could just leave that one blank. So maybe that's a way to use the box diagram to show the possible outcomes. Just block anything that couldn't happen, like blue, blue is not possible if we're not replacing, and yellow, yellow is not possible, and orange, orange is not possible, and green, green is not possible. So I think there may be a couple of effective ways to use this sort of diagram that you can still see the 30 possible outcomes, and you can either eliminate options that aren't there, or you could go ahead and just label them the inside options based on the other second draw. So play around with that. Remember, visuals are meant to help us. There's not any one way to use them. They're meant as tools to support us. So as long as it functions, then it's a good visual. So back to our answer. Let's make sure we solve the problem entirely. Did we use multiplication or addition? We used multiplication because we wanted to find the chance of a chance, essentially. You can think of it as a part of a part of pulling red and then blue. So there's a chance that this isn't red in the beginning. So in that case, our successful outcome experimentally is 0, but there is this one chance that it's 1/6 red and then 1/5 that we get blue. So we're finding the chance of a chance, if that makes sense. And we can really see that with our tree diagram. On the off chance that this is our first pull, this is the second chance of it being blue. 1 in 30 outcomes should be that order. And that was problem 4.